In this lesson, I'm going to be talking about the kinetic molecular theory of gases. Now, the ideal gas law tells us how gases behave. So just as a review, as pressure increases, the ideal gas law tells us that volume decreases. As temperature increases, pressure increases, and as temperature increases, volume increases. Now, the kinetic molecular theory tries to explain why gases act the way that they do. And so there are a total of 5 different postulates from the kinetic molecular theory, and a lot of these will probably be familiar. The first one is that gases consist of a large number of molecules that are continuously moving and are moving in a random fashion. So there isn't a predetermined course. They're not going in a straight line for a predetermined destination. They are moving randomly. The second theory is that the combined volume of all of the molecules of the gas is negligible relative to the total volume of the container. We'd already talked about that, the fact that the volume of the gas molecules is extremely small to the point at which we ignore it when we're looking at the total volume of the container. The third theory is that the attractive and repulsive forces between gas molecules are negligible, and we'd already talked about that as well, the fact that gas molecules aren't attracted to one another. The fourth is that energy can be transferred between molecules during collisions. Now, the important thing about this is that energy is not lost, therefore these are elastic collisions, so one molecule might transfer its energy to another one, but energy is never lost during these collisions. And the fifth one talks about average kinetic energy, which is a topic that we're going to spend most of this video talking about. Now, average kinetic energy is proportional to temperature, so I like to use the acronym TAKE. Temperature is average kinetic energy. Now, two gases at the same temperature therefore have the same average kinetic energy. So if temperature doubles, the average kinetic energy will also double. Now, if you look at these two graphs right here, what this demonstrates is that every single molecule in a gas does not have the average kinetic energy. They don't all have the same kinetic energy. They can have a wide range of energies, as is represented in A right here. That bell jar shape of the graph demonstrates that molecules can have speeds ranging from 0 all the way to 10 times 10 to the second meters per second. However, if you look at the majority of the molecules, if you look at the blue graph, which is at 0 degrees Celsius, most of the molecules have a lower molecular speed if they're at 0 degrees Celsius compared with 100 degrees Celsius. You can see that difference right there. Another thing to keep in mind that this graph notes is the fact that at 0 degrees Celsius, fewer than half of the molecules have speeds above 500 meters per second, while at the 100 degrees Celsius, more than half have a speed greater than 500 meters per second. And so what that tells you is that while all molecules might not have an extremely high speed, on average, more of the molecules at higher temperature will have higher kinetic energies. So average kinetic energy, we'd already talked about the formula for kinetic energy, which is 1/2 mv squared. The velocity now for the average kinetic energy, we represent that with that u symbol instead of v. That is the root mean square speed. So that is the speed that a molecule would possess if it had the average kinetic energy. Now let's talk further about understanding gases and the way that they behave. First of all, pressure. When we're talking about pressure, pressure is caused by molecules colliding with the walls of their containers. Next, the effect of an increase in volume at constant temperature. If you increase the volume, what happens is that pressure decreases. Now, we know that from the ideal gas law. However, let's understand why. Well, molecules, if you increase the volume, they have to travel longer distances, and therefore they're going to collide with the walls of the container less frequently, and therefore pressure is going to decrease. The next behavior that we assumed is the fact that increasing temperature will increase pressure. Well, let's understand why. If you increase the average kinetic energy by increasing temperature, that means that molecules are going to collide with the walls not only more frequently, but also with more force. So that will cause the pressure of the gas to also increase. So kinetic molecular theory enables us to actually understand why we see the patterns that we did in the previous lesson. The next two characteristics that we're going to talk about are effusion and diffusion. Now, before we get into these terms, there are a couple more concepts that I need to talk about. The first one is that the kinetic molecular theory states that at a given temperature, the average kinetic energy of all gases is going to be the same. And so as a result, while the kinetic energy might be staying the same, the average kinetic energy might be staying the same, that does not mean that the root mean square speed stays the same. And so as a result, what affects the speed, the actual speed of gases, is actually the size of the gases. So logically, it would make sense that larger molecules would travel slower. So this formula right here, that quirky m, that is the molar mass. So as you can see from this relationship, what this tells you is that the larger the molar mass, the smaller the root mean squared speed is. So the lighter molecules will therefore travel faster than the heavier molecules. So if you look right here, if you look at this graph, what this is showing you is oxygen compared to all of these other molecules and elements. Oxygen is the heaviest, and therefore most of the molecules of oxygen will be traveling with the lowest molecular speed, while hydrogen, for example, has molecules, most of its molecules traveling at a much faster speed. And the reason why is because of the difference in molar mass, the difference in size. Now let's actually talk about effusion and diffusion. Effusion is the escape of gas molecules through a tiny hole. So here's one great diagram to represent that. You see all of the gas molecules moving in a container and then a tiny hole in the center of that red circle. That small hole enables once in a while a molecule to move through. Another example of effusion that you experience in your everyday lives is with a balloon. If there's a little hole in the balloon, which there are a lot of, then gas molecules can move through that tiny hole. That process is called diffusion. Diffusion is the spread of one substance through either space or through a second substance. So you experience diffusion when you smell perfume because the perfume is moving through air. Graham's law of effusion enables us to quantitatively investigate the process of effusion, and Graham's law actually also works for diffusion as well. So if you look at this formula, R1 represents the rate of the first substance over the rate of the second substance. If you notice, they're inversely related to their molar masses, the square root of their molar masses. And so what that helps you to further clarify is the fact that if you had, for example, an argon balloon and a helium balloon, then the helium balloon would lose its gas through effusion much faster than the argon balloon because it has a much lower molar mass. So Graham's law of effusion shows you that fact by showing this equation right here. Now, the way that we actually express this, if you see a value for R1 over R2, what this tells you is that, let's say, for example, I had the rate of carbon monoxide over the rate of nitrogen monoxide. If that value is 1.035, the way that we would express that is the fact that the rate of effusion of carbon monoxide is 1.035 times faster than the rate of nitrogen monoxide. So I'll actually show you an example right now, but that's how we express that value, the R1 over the R2. All right, so if you look at this example, it tells you have an unknown gas, and it's a diatomic molecule, so that does matter when we're trying to determine what exactly the gas is. And it effuses at a rate that is 0.355 times that of oxygen at the same temperature, all right? So what that tells me is that the rate of effusion of that diatomic molecule equals 0.355 times the rate of oxygen, which I showed mathematically. It's important to be able to take those words and put it into a mathematical equation. And so better stated, Rx, the rate of effusion for that unknown gas, over the rate of oxygen's effusion equals 0.355. So now I can actually plug it into Graham's law of effusion to find out what molecule I have. So I'm going to take Rx over R of oxygen, and I'm going to set that equal to the square root of the molar mass of oxygen over the molar mass of X. Keep in mind that you need to switch those molar masses because there is an inverse relationship between the rate of effusion and the size of the molecule. So I know that Rx over R of oxygen equals 0.355, and I know that the molar mass of oxygen is 32 grams per mole. And so what I'm going to solve for now is mx. Keep in mind, unfortunately, my program doesn't let me do this, that it's 32 over m, the square root of that entire value. So what I need to do first is I need to square 0.355 to get rid of the square root sign. I'm going to set that equal to my 32 grams per mole over the molar mass of my unknown substance. Now I'm going to multiply the 0.355 squared times my molar mass. I'm going to set that equal to 32, and then I'm going to solve for my molar mass of my unknown substance, which is 254 grams per mole. Do keep in mind that this is a diatomic molecule. Therefore, I need to divide the molar mass by 2, and what I discover is that my unknown diatomic molecule is actually iodine.